And we are live. So now I mentioned that today we might discuss the what is a result which is known as the fundamental theorem of calculus. So let me just share this window here. Okay. So today is basically the last day that we use this calculus volume 1. There are two things that you might want to do. One, you might want to look at this table of integrals. Just a second. This is fairly handy, Appendix A of Book 1. So you will find this table of integrals. There are some trigonometric integrals and things like this that you can find here. There are plenty of those. You can always refer to this table if you want to calculate certain integrals, and you're at liberty to use any and all of these. If you do, just mention how you used it and so forth. Here you can find how to find the integrals. These are indefinite integrals, of course, but we talked about the definite integrals. And this table of derivatives and the derivative rules as well. Again, you are at your liberty to make use of all of these, so that there is nothing here that is none of this you have to memorize. And when we have the exam, you know, you can use any and all of these tables here in the book. These are all at your disposal, so you don't have to learn them by heart. All right, so today we will be talking about the fundamental theorem of calculus. But before we can go to the fundamental theorem of calculus, I would like to revisit or visit one topic that we skipped just briefly, about minima and maxima. So minima and maxima, also known as extrema. So this comes from, let me think. I think it comes from Latin. Minimum, maximum, that's the singular. Maxima, minima, that's the plural of. So minimums and maximums, if you like, and extremums, extreme points, known as the extreme points. So if we consider, here's the one function, considering the function which is a parabola, opens upwards, parabola x squared plus 1. And it has a minimum at 0, right? And its value is 1 at there. But it doesn't have a maximum in the real numbers because it just grows and grows on. So this is very common. We have functions that they have a minimum, but no maximum, or they have a maximum, no minimum. And sometimes they have neither. Usually we are not interested in maximums and minimums in the absolute terms. We are usually interested in them in relative terms and or in a certain interval. And here the definition of a maximum is, or maxima, absolute maximum, absolute minimum, or absolute extremum, meaning either maximum or minimum, is with respect to some interval I. Often we take this interval to be the whole real numbers or the whole domain of the function, but not always. Later, if you study optimization, then usually what we're looking for is either minimum or maximum in some constraint set, which is not the domain of the whole function, but somehow constrained by other constraints. And we're not going to talk about that in this course of that much. And we know there's certain things. It has to be understood that absolute meaning among all possible points in that, it is absolutely the smallest, and it means that there is no largest. I mean, if we have or no larger or no smaller, depending on whether we're talking about maximum. So look at this definition. F has a maximum at C if f at C is greater than or equal to f at x for all x in your interval. So, there's nothing that is larger than that. And it's an absolute minimum if there is, smaller. It's absolute maximum if there's nothing larger, and absolute minimum if there is nothing smaller than that. And this is, should make complete sense in this case. And there are some examples here, not going to go in depth into here. So for example, the 1 over x squared plus 1 has an absolute, in the real numbers, it has an absolute maximum at 1. It doesn't have a minimum. It does approach 0, but it never reaches 0. So it doesn't have a minimum. So not having a minimum or not having a maximum doesn't mean that it's not bounded. That's important to understand. If a function approaches 0, just like this, goes towards 0, but never quite reaching it, or goes towards some number from below, then it doesn't have that maximum. It has a bound, an upper bound, and its limit at infinity may be that, but it's not the same as a maximum or the minimum. You have to understand the difference between a limit and a minimum or maximum. And the cosinus function, for instance, is as a maximum of 1 and minimum of -1, and these occur periodically by intervals of 2 pi. So here are examples. Here's one function which is defined piecewise. So this is an open interval. So it approaches this point, -2, never quite reaching it. So it has no minimum, right? Because it can get smaller and smaller here, but it never quite reaches this 2. So that's important to understand, that even though there is a limit, it may not be the minimum or maximum. So here's another example. Here's a function. It has a minimum here at 0, and it has the maximum at this x equal 4, because that's the end of the interval that we are looking at. So extreme values are found either at the ends of the region or somewhere in between. So we don't know which one is, or they're never found because we can never reach them. And the extreme value theorem, which is important to understand, is that this is what we need here, is that if we have a continuous function over a closed bounded interval, closed and bounded interval meaning a and b are both finite, it doesn't extend to infinity, so it's closed and bounded, then at some point between a and b, or possibly at a or b, f has a maximum and f has a minimum. So if it's continuous, then in a bounded set, is that a closed and bounded set, it has a minimum and a maximum. That needs to be, it should be clear, right? So there's only this, well-defined interval. We look at the edges. Is it the biggest there? No, then it's the biggest at some point between, and the smallest are the same way. And here, to understand the so-called critical point, concept of critical points. So if it's continuous, then there are, where can we find these minimums and maximums? Well, there are 3 possible cases. One, that's at the beginning or the end, so at the edges of your interval. If it just keeps on growing and until it hits the walls, and the maximum may be there. 2, it may be at the 0 of the derivative, because that's where the function is flat, so it goes down to the left, down to the right, maybe. And 3, at points where it's not differentiable. So if it's not continuous, then maybe it doesn't have a minimum or maximum. Then we can't say anything. But this is continuous, but it's not differentiable at here. There's a corner point there, so it's not. So we have to look at all these points, and in order to find the minimum or maximum, we have to look at this point. Let's say that this is the, well, if it's defined from -infinity to infinity, then we have to look at whether it's going in here. It doesn't have a minimum, global minima anywhere, because absolute minimums, because it goes to negative. It seems to go to negative in both sides. Locally, it has a minimum, meaning that we can draw some kind of a interval around this point, and then it will be a minimum at that point. So local minimum meaning that if we compress our interval around that point enough, then that will be a minimum. That means local minimum. But these concepts should be familiar, but look at these. So again, a critical point is a point where either the derivative is 0 or it's not defined. And for a differentiable function, a local extremum is always a point where the derivative is 0. Local meaning that, you know, you can take an interval and it's in between, and if it's a minimum or a maximum, that the derivative is always 0 in there. And I'm not going to go into the proof. So this is what we need to discuss today's topic. So I'm just assuming that this is stuff that you know, but just if it's not, then please read this chapter 4.3. Okay, now let's go to today's main topic, which is the fundamental theorem of calculus now. So what is the fundamental theorem of calculus? We'll need to discuss some things, like we have to discuss the mean value theorem. Mean value theorem we talked about already, and what does it mean for integrals? Then we have to talk about that for integrals. So for integrals, the mean value theorem states that if we take the integral from a to b f of x and divide that by b minus a, then we know that there is going to be a point in between a and b such that the f at c is equal to this average. So think about it. This is the average, this integral from a to b f of x dx. You can think of this as the average value of f between a and b. So the length of the length of the interval, the area under the curve divided by the length of the interval. So if you think about it in terms of the area, and again, now I'm not having a paper and pen here, so I have to go to this other place. So anyways, if you think of the functions integral as the area under the curve, so you can think of this as the average height of the box. I mean, remember that we thought of this as the limit of those smaller and smaller boxes, and we calculate the height of that box, and we add the areas of these boxes. So you can think of this as simply the average height of the boxes, which means it's like the average value of the function. And there is a point in between a and b such that this f at c is exactly equal to that average. We can also state this in such a way that there is a value in between a and b such that when you calculate the integral from a to b f of x dx, then that's going to be equal to f times c times b minus a. So again, this can be understood in such a way that if we, just a second, I'll go get a piece of paper, then I can draw you a picture. It seems that I had paused the recording while I got that. Well, never mind. Sorry about that. All right, let's move along. We've now covered the fundamental theorem of calculus. Basically, two parts. Firstly, this one which probably you already knew. To find, you can find the definite integral by finding the antiderivative at b and antiderivative at a of this f of x, and then subtracting. And also the part one of the fundamental theorem of calculus, which was this. And then again, remember that here, look at the examples of this and how to use the chain rule and the fundamental theorem to find derivatives of certain functions as defined by integrals. We sometimes have to do it when we move towards the differential equations. So I mentioned here in this week's curriculum that you should read chapters 5 and 6 from Calculus 1. Even though I say here that you should read chapters 5 and 6, the reason, I'm just going to go here up and show you the, oh, I accidentally skipped. So 5 and 6. When I say 5 and 6, I'm not expecting you guys to read, you know, all of this. Just look at some of these applications. No need to spend too much time on there. Here are some integration techniques that we will look at now. So one technique, so when we have this, did I have this? No, I just go, just a second, I'll show you the table. So when we have something simple inside the integral, then we can look, we can consult the table of integrals, so which I will open here. So we can consult the table of integrals here to find the antiderivative of most functions. But of course, these are just your very rather typical fundamental elementary functions. And then, you know, it's quite many of them here. But really, I mean, first of all, you can't make a table out of all possible integrals, obviously, because there's so many integrals that choose from. So we need to be able to use some rules on how to establish the integrals, or you know, how to establish the antiderivative if we are to use the fundamental theorem, the evaluation theorem, to find the integrals. And one key trick, and trick it is, mind you, the one, just before I go here, I just wanted to make one disclaimer. One of the problems is that when integration is basically finding the derivative in reverse. So you have asked to find the integral of something, and we need to figure out what the function is. What is the function whose derivative is this? The problem being, of course, that while the derivative is usually easy to find, going back is not easy. And one of the reasons is it's not actually it's not actually bijective. It's not two ways, right? Because there are several different functions whose derivative that may be. Of course, I mean, they all differ only by constant, but you know, how do you express them? That's one thing. So if we consider something like we have a polynomial function inside the integral, and we need to find the integral to that, then sometimes it's easiest to reconfigure or rearrange the terms in such a way that we get to a familiar form, such as the form found in the chain rule. Like, you know, if we have here a function, an inner function, gx, and then g prime of x, then really what this comes to, whose derivative is this? So the substitution, we want to find a substitution in such a way that we can kind of immediately see that this is of the form f of g of x times the g prime of x. And then we just substitute this g of x with u, and we can find the integral of this f of u, because this g prime of x dx is the du. So let's go back to this. Why do we write this g prime of x dx? So this, remember that this dx, it stems from this delta x, this small change in x. And now, if x changes a little, how much does g of x change? Well, the g of x changes by this much, plus, of course, the tiny, teeny error. But when d of x is already thought to be the limit of that delta x going to 0, so this is the proportionate change of g of x when x changes. And if u is g of x, then this g prime x dx is in fact a tiny change in u as per, the proportionate change of x. So here's a proof of it, and it's not really, I mean, why would we need to prove? We apply the chain rule to this, and we get this f of g of x, g prime of x. So here you should probably look at this problem-solving strategy, integration by substitution. So if we are to detect that there is some function and we sniff that its derivative can be found there, then, let's do that. In this case, the integral of something 3x squared plus 4 to the power of 4 times 6x. And we notice that, okay, here's some function, something to the 4. That something is 3x to the 2 plus 4. And we notice that 3x to the 2, its derivative is 6x, and we can find it outside here. So we just use our u as 3 times x squared plus 4, and then we notice that this becomes this 6x dx is in fact du. Again, you can find this. This is I'll just write it in the chat window. If you are uncomfortable with this, where does this du equals that come from? Then if I write that u is equal to 3x squared plus 4, then I can write that du per dx is equal to 6x, and then du, I just multiply both sides by dx, so it's 6x dx. I think this is a slight abuse of notation, but you are at your liberty to do this. So I'm giving you the go ahead to do this if you want to remember how it's done. So this just means because u is 3 times x to the 2 plus 4, then a minor change proportionately, a teeny weeny change in u that results in a teeny weeny change in x proportionate to x is 6 times x. So in order to change u by a teensy bit, when we change x by a teensy bit, then u changes by 6x dx. Right. And you are at your liberty to do this when you are finding this differential change, or this du and dx. All right. Here's another situation. In this case, we don't quite have the derivative of z squared minus 5, right? We don't quite have it in there, but we have z. If we take the derivative of z squared minus 5, that's 2z. But in order to get this 2z there, we'd have to multiply this by 2, but then we also have to divide it by 2 in order to balance it out. So this z is really, you got to understand that this du is 2 times z dz, then z times dz is really 1/2 du. So that's why we get this 1/2 in front, and this is simply u to the power of 1/2. We find the integral of that and then substitute u back. This is a very common situation. Here are some examples. Very common ground or very common place for using the substitutions is with trigonometric functions. So trigonometric functions, This is very, very, very common ground, especially rational form trigonometric functions. Really nasty to often find, but then with a clever substitution works sometimes. Don't be fooled, however. You can't always find a substitution that works. So, you know, I'm not a big fan of the idea that you learn all these substitutions, then I give you exercises, a lot of exercises where you just have to find a clever substitution. We'll try them out a few times and a few examples, but I would not worry too much about that. The tricks of that doing by hand were kind of like not, we don't want to cultivate the idea that mathematics is about these teensy beansy tricks that we use. Of course, they're handy sometimes and it helps you in thinking, your thinking and thinking about it, but it's not really some kind of thing, especially because it doesn't always help you solve it. That's the one thing. So here's a question for you. I'm going to now divide you into groups. We'll have about 10 minute or so break. So do this exercise 5.27. Use the substitution to evaluate the integral cosinus of t over sinus of t squared dt, and figure out what substitution to use. There's a sinus there, there's a cosinus there. One is the derivative of another, so maybe think a little bit of how you can express this a little bit better, and look at these examples above and so forth, and do it in groups. So I'm going to put us in pause, and so that if you're going to use the substitution here, then remember that very well, that if it's a definite integral, then also remember to substitute at the limits, because otherwise you get a wrong answer. I mean, the good rule of thumb is to think about it. Okay, my new variable is u, which is g of x. If x gets the value between a and b, then what values does u get? Well, between g of a and g of b, obviously. I'm not going to prove this theorem here. There are certain problems to this. It's not entirely void of problems. One should be aware that you know, I mean, if just obvious situation, if you substitute some function that cannot even have these values that you will get, like, you know, if you have I don't know, if you have polynomials and then you substitute for sinus of something and something like this, then you may run into trouble. Just make sure that those functions actually appear in the similar function actually appears in that. So I'm not going to make a problem of it, and just use this. There is several examples of here, exponential functions and things like this. Word of warning, sometimes you will encounter something like e to the power of, and then there's like a polynomial here. Unless there is an actual, unless you can actually find the derivative, or, you know, something that has the same degree as the derivative of this in here, then these won't always work out. So e to the x squared, for instance, you won't find a substitution for that unless you have that x in front. Here's another examples. I'm not going to go into these with trigonometric things and so forth. So let's move along. Here are exponential functions. Exponential functions are fairly easy and fairly benign. Remember that you need the logarithms to, usually we will only have e to the power of x, e to the power of something that we deal with here. So it's not going to be a huge problem for us. Not going to go into details here. Again, these are a little bit contrived examples when x squared and e to the minus something, because a to the x to the 3, because then very often, like I said, very often these are some things that you cannot just, you just can't do that. You know, one example would be e to the power of x squared. So if you try to find the integral of that, you won't be able to do so. So, but you know, if you can do a substitution that you find the derivative of the exponent here, then that works for fairly well. Here are other examples like this. Not going to go here. The substitution is usually something like, you know, some function here that appears in the exponent. That's usually the way you can solve this. Like I said, these are very good material for self-study, so we're not going to go here into these. Let me see. I just go back to the should have probably had. Okay. And there's integrals involving trigonometric functions. Let's look at that a little bit. So one thing that we didn't discuss, I put it in the exercise this week. Remembering that these involve the inverses of trigonometric functions. I mean, the inverse of sinus, the arcus sine. There appears this term 1 over the square root of 1 minus something. The reason for this is easily derived. I mean, if you take this, let's say that f of x is the sinus of x. If you take f of x to be the sinus of x, then the arcus sinus of x is the inverse of that. And if you find the derivative of it, remember that there was the inverse, the derivative of the inverse. So if we are to find the derivative of inverse, I don't remember if you remember it. So d over dx. Let ux be the inverse. I'm using ux because I'm writing u of x instead of f minus 1x because it's shorter to write. So then d over dx of ux. Well, that's actually equal to. We need to find the derivative of that, right? Now, one thing to understand is we can derive this from the fact that we have that f of u of x is x, because u is the inverse of f, then f of u of x equals x, right? Let's find the derivative of this. Thus, d over dx of f of u of x must be equal to 1. I mean, if f of u of x is x, then the derivative of f of u of x must be 1, right? The derivative of x being 1. And now we can rewrite this as f prime of u of x times u prime of x equals 1, right? From which we get u prime of x is equal to 1 over f prime of u of x, right? So here we can write, let f of x be the sinus of x, right? Then u is the arcus sinus. I'm not going to. So what is the then f prime of x is equal to the cosinus of x, right? right? So, but remember, assume, so what is the sinus of x? And let's assume sinus of x is greater than 0. Let's just assume that this is so. Then remember, sinus of x squared plus cosinus of x squared is 1, right? So we get that the sinus of x squared is 1 minus cosinus of x squared, right? And we get that the sinus of x is the square root of 1 minus cosinus of x. Okay. Sorry, cosinus of x squared. Sorry, I forgot the squared there. And alternatively, we can say that cosinus of x is, it's plus or minus, but I'm going to write here just so we get right. So from here, if we remember that we have 1 over square root of 1 minus u squared, right? And substituting all that, remembering u is oh, sorry, I used the wrong term there, symbol there. Oh, I'll leave that rest to you. So you can actually prove that this the derivative of the arcus sinus is this. I'm not going to do that. The inverse of sinus you can get. So okay, homework, which I think I put in this week. So I'm not going to. Homework, show that the d over dx of sine of is equal to 1 over square root of 1 minus x squared. You can do this using the inverse rule, but I showed you some of the things that we need to do to figure it out. But I'm not going to spend time here. I'm not going to spend too much time here. All right, here it is. Here is actually, well, here it is actually the proof, but I'm not going to go there in detail. All right. Trigonometric functions, very often the case, these inverses of trigonometric functions. When you see a square root of something minus something x squared, usually substitution will give you the inverse of the cosinus. If it's something plus something, then you get the arcus tangent. I mean, those of you who might study machine learning at somewhere, you know, these so-called sigmoidal functions often appear. This could be familiar to you, but then also the arcus tangent, the inverse of the tangent function. The inverse of the tangent function is great because, you know, when you extend to the minus infinity and the infinity, it's bounded and it's between pi over 2, minus pi over 2 and pi over 2. If you normalize it by dividing it with pi over 2, you get a function that is between minus 1 and 1. Approaching 1 at infinity and minus 1 at minus infinity, and those are usually very often used, and their derivatives are looking like this. So here's the 1 over something plus x to the 2. So here you can applying those formulas, you find that this inverse of tangent function appears there. These are fairly benign functions that can be, integrals can be found fairly easily. But in general, if you have a very complicated rational function where there's a polynomial over polynomial, then those tend to be really hard, and we're not going to spend time on those. These simple ones, usually, yes, fine, but more complicated ones, not going to spend time on those. That basically finalizes the whole of the book. I mean, I wrote here that look at chapter 6. I'm not going to talk about chapter 6 here, especially not going to use the hyperbolic functions. They can always be expressed using exponential functions. Growth and decay, moments and center of mass. These considerations are not going to go here, but the moments and centers of mass, these are in fact considerations that will be relevant if you study probability calculus later. In probability calculus, similar calculations as these centers of mass are needed. And they actually, the center of mass calculation conforms to the, I mean, it's exactly the same thing when you calculate the expected value in a distribution, and the moments, the moment of inertia, and those, they correspond roughly to the calculation of the variance of the distribution. So this is something that you might want to study. I'm teaching that course in the spring, so I'm going to revisit this topic there, and it will help you. I'm not going to ask this in the exam, but it will help you if you look at these. All right. But basically, that's what finalizes our discussion of this volume 1 book. So just very quick recap of what we covered and what I expect you guys to read. Chapters 1, 2, 3, pretty much all of them, except for implicit differentiation. Implicit differentiation, not going to ask anything about it. Of chapter 4, minima, maxima, and the mean value theorem, a little bit of those, look at those. I'm not going to ask you to find the minima and the maxima, but you should understand that the basic theorems, like for instance, the continuous function gets its minimum and maximum value on a closed and bounded interval. Mean value theorem, we talked about several versions of this, so that there was the intermediate value theorem, which is like the simplest one, so that if a continuous function and it gets the value fa and it gets the value fb at ends of the interval from a to b, then all the values that are between a and b will appear as functions of value. That's the intermediate value theorem. The mean value theorem then states that if you have I think it's best understood in terms of finding the tangent, so that if you draw, just very quick drawing here. So if you have a function that goes like this, I'm going to draw a picture here. The intermediate value, the mean value theorem, meaning that if you have a function at f of a and f of b, and then you draw a straight line, then there is a point C there that has the derivative, whose derivative is exactly f at a, f at b minus f at a over b minus a. And then, as a and b approach one another, approach the C, then this comes down to the definition of the derivative. And then the same thing, of course, always we were applying this for the to find the fundamental theorem of calculus. We used that was applied in there. All the rules here you should learn from chapter 3. Like I said, L'Hopital's rule, the limit of f over g when f approaches 0 and g approaches 0. The proof is more important. Understand why we can say that in order to find the limit when that goes to 0 over 0, then you can just take the derivative of f over the derivative of g. That proof was the thing that I would like you to understand, because that kind of teach you on why and how we can use the calculus. L'Hopital's rule is very useful in finding the limits, but we're not going to talk too much about that. Then integration, really the idea of the Riemann sum, that was the important part, the definite integral, but understanding that then we tied it with the fundamental theorem of calculus and the version 2, the evaluation theorem. We kind of brought it together so that you can find the antiderivative and it evaluated at those points. And from now on and from these on, I mean, this latter part, this rest of this lecture, we already talked about the substitution rule, but that was there. Now we move to the volume 2, in which we have more rules for integration. So study these, but we now move to calculus volume 2. Sorry. The chapter 1 in this calculus volume 2 is basically the same as chapter, was that 5? Yeah, and chapter 6 and 2 here are basically the same. So we're not going to revisit them now. We move straight to chapter 3, techniques of integration. And this is technical stuff, practical stuff on how to find integrals. So this is not, I don't put a very large focus on this. Learn this and figure it out. Because if I put in the exam, find the integral of this, find this integral, and you just punch the numbers into Wolfram alpha, and then you get some number and you say, this is what I got, then that's not worth much. And I really do urge you not to get the paid version of Wolfram alpha that shows you the intermediate steps and then you claim that that's how you did it. I'm not going to put anything too hard anywhere. I just want you guys to be able to understand most of these things. And we have these rules, they're not that hard. And don't memorize them as such. Probably better to just learn to justify the rules, and then you will remember them because you remember how it was constructed. Just like I showed or wanted to talk about the chain rule in last week's exercises, how to quote prove that the chain rule applies. Then in a similar manner, these integration rules, they're all rooted in those differentiation rules. And when we learn those differentiation rules, not by just rote memorization, but by understanding why they work the way they do, then these integration rules are also easier to understand. So let's go into this. These partial fractions, the numerical integration, let's see how much we talk about this. The integration by parts is really, I've noticed that a lot of the time people don't understand what's the idea of integration by parts. And I wouldn't learn I wouldn't even try and learn the formula for integration by parts. I would remember that, oh, there's this thing called integration by parts, and it's doing the product rule in reverse. Okay? So remember, let's take the product rule. Let's look at it a little bit more closely. So let's take h of x equal to f of x times g of x. Then we obtain its derivative, which is f derivative g plus g derivative f. And now we find the integral of both sides. We find that f times g is the integral of gx f prime x plus the integral of fx g prime x. And if we write this as, if this f times g prime. If this is the integral we are looking for, we can express this by looking at it like this. And sometimes this is easier to solve than if we notice that we are, look, we have a product of two functions. One, f of x, don't know what to do with that necessarily, times g of x, sorry, times something which we immediately see to be the derivative of some g. And it looks as though the derivative of f is relatively easy to find. Then we can use this integration by parts formula. But, you know, to figure this out or to remember this, it's best, perhaps best to think about this as a, you know, let's find the derivative of this, and then it's just this plus that. It's easier to remember than remembering the integration by parts. So here's an example. We have x times the sinus of x dx, and we need to find the integral of that. So we have x, fairly easy. We have sinus of x, again, fairly easy, but their product is a bit harder. So let's call this x equal u. So we have u, that's a function of x. Well, it's the identity function, the trivial function of x, ux equals x. And then this v, which is sorry, this we consider then sinus of x as the derivative of something. The derivative of what? Well, the derivative of the negative of the cosinus of x. So we have integral of u dv, which is sinus of x d of x. And this, I think this is a little bit stupid, the way this is done. I think it's a little bit silly. Honestly, I think this is not that much, doesn't make much sense. I think it's better to think of it this way, that we have f of x equal x. We have g of x equal sinus of x, g prime of x equals sinus of x, right? Using this, this formula here. And then the integral of x times sinus of x dx is then f times g. So that's, well, g prime, because g prime of x is sinus of x, then this implies that gx is, well, what is the function whose derivative is the sinus of x? That's the negative of the cosinus of x. So we have the integral is the x minus x times the cosinus of x minus the integral of sinus of x, sorry, minus cosinus of x times, well, what is the f prime? It's 1 dx. So the latter part is easy because then we have the cosinus of x there. We have the integral here. Here it's really integration by part formula. I mean, I think this is a bit confusing here. Just this is my f of x. This is my g prime of x. So this is my g of x. That's my f of x. Here's my g of x. There's my f prime of x. That's 1. And I do the simplification, and I find that this is minus x cosinus of x plus sinus of x plus c. Here are some examples. Evaluate this using integration by parts. The question here is, you should read these ideas of natural questions to ask, how do we know how to choose u and dv? Sometimes it's a matter of trial and error. Here are some ideas for guesswork. LIATE. I don't like this this idea. This a little bit too much maybe emphasizes the idea that integration, well, the fact. It emphasizes the fact that the integrations of these kind of formulas requires a large bag of tricks to be able to solve them. I'm not a big fan of that idea. I think it's a good idea to learn them. It's manual labor and as such good for the human spirit. But like all manual labor and all hard labor, it can be crushing to the spirit as well as educating. So that if you get thrown into the deep end with these, then it's quickly get frustrated and feel like you don't have a clue as to what's going on. When it's really not much understanding is involved, it's more like playing with a sleight of hand. This is a lot of the stuff that I see when mathematics is being taught. I see a lot of the time is that people are being taught rules and that you should memorize and techniques that you should memorize, and people come to this idea that learning mathematics is learning these tricks and rules, when in fact you should probably try and understand the techniques by which we prove these rules correct and not the rules themselves. The way of thinking behind it. So I'm not going to go to this mnemonic part here, but study these examples in great detail. I didn't put any integration in parts in this week's exercises yet. And here's a warning example of why this idea doesn't work. There's one situation that is fascinating. There are some situations where you can do integration in parts, and you can come up with recursively come up with a situation where you have the original integral here, and then moving everything to the left. This I is that sinus, and then I is the integral to I, and then you can figure out that the integral is in fact that. That's actually a neat thing that happens. So sometimes this is a way that you can get a result, is that you do the integration by parts, then you arrive at another situation, do the integration by parts again, maybe, and you get the same integral. But the sign has reversed. It's like minus. And if you get the same integral, something, and the same integral on the other hand side, then very more often than not, that just cancels out, and then you are left with a function that is identically 0, and you get nowhere. But if the sign changes, so as it happens, if there's a trigonometric function involved, often the sign changes from minus to plus, or plus to minus, and then you get the situation where you have an integral on the left hand side, something minus the integral, in which case you get 2 times the integral is equal to something, and you can solve the integral. It may feel a little strange at first, but that's not actually uncommon. We'll see this a lot when we start talking about the sums and the series and convergence. Also, a worthy thing to note is that if you use the integration by parts on the definite integral, make sure that you use the substitution or, on this part. So evaluate this integral in this part because that's already come out of the integral here. And this must have the limits from A to B. I'm going to put some of these exercises for not this week, but for next week. We're running a little bit behind on the exercises, but that doesn't matter because in the last week it all comes together. It's not that big of a deal. So this week you should probably look at this integration in parts a little bit more carefully. Here are examples of what to do with trigonometric functions. So in trigonometric functions, you usually use substitutions. For instance, here's something cosinus of x to the power of something times sinus of x. So you notice that the cosinus can be marked as u, so that du is the sinus times dx. That's fairly easy to do, and you can evaluate these as well. There are other situations where you can have other powers of cosinus and sinuses. I find these, again, as examples, somewhat contrived. Please feel free to study them, but I'm not going to spend an inordinate amount of time on this because I find that, this is like a rabbit hole. You can go down as far as you like and learn these rules a lot. Study this, look at the examples once. Don't worry about memorizing any of this. You can then consult these techniques if you encounter this. I think that's far better is to just study these a little bit, go through them once, you leave the memory trace of, oh, I know that this I've seen this being done, and then you can consult the book. It's far better use of your time than trying to memorize these and trying to remember which rule was which and being able to do that. No one wants to work like that. If you have to do this at your work as an engineer, then you'd consult the relevant books and even software in order to do that. Why you need to learn these things, how they are derived, is that you don't just blindly go and apply some rule and not understanding when and if it can be applied. Not particularly interested in going through these techniques here. So this is a little bit, I think this is tantamount to bullying, the idea that you have to do this. There are again, like I said, there are situations where you can use trigonometric substitutions. That's often the case when you have these functions in which you have the square root of a second order polynomial. Then sometimes you know for a fact that this is limited to some region, like in here, x can only be between minus a and a. Sometimes, you can get away by substituting a with x with a trigonometric function. But you have to be cognizant of the fact that if you just substitute x with sinus of x, for instance, the sinus of something theta here, then obviously that doesn't get all the values that x could get. Because x could be between minus a and a. If you just put there the sinus of theta or something like this, then that only gets from -1 to 1. So for instance, here is the 9 minus x to the 2. So the reason why you want there to be a trigonometric substitution where you factor in the room of maneuver for x here. And one of the reasons is I want you guys to understand that that's the reason why we do this. It has to get all the necessary values. So Yeah. And these are fairly nice and handy tricks. You can then find these and eventually when the dust settles down, you can get something like A and B and so forth. Here's some justifications and here's a problem solving strategy. You can learn these. This is perfectly fine. Learning these problem solving strategies. You don't have to remember all of them. Just learn that this is one of the tricks that you can do and then, you know, just forget about it. And then when you encounter a problem, you know, go back to the book and see, okay, I think we might try this. Let's see if it's that. It's much better than trying to learn this by heart at this time. So here are some of the situations. Again, not a huge fan of use of such because we're not practicing this kind of art theater. Partial fractions, okay, fine. The partial fractions, meaning the situation is where we have a rational function. So there's a polynomial over a polynomial, let's say. Then if we can find the factors of the denominator, in this case, x squared minus x minus 2, it has the roots 1 and minus 2. And so it's got factors, you know, the x squared minus x minus 2 can be expressed as x plus 1 times x minus 2. And then we can find a partial fraction here. They didn't talk about that, but the common denominator. So, you know, if you have a p of x over x minus x plus a times x minus x plus b, say, let's say it's like this. Then we can try to find, you know, a over, not a, let's call it u over x plus a plus b, v over x plus b. You know, if we have something like this, solve that for u and v, so that it matches, and then you can come up with this. This is, I mean, if you find the common denominator of these, this is simply a refactorization of that, and then you can integrate this and integrate that. I'm not going to do this partial fraction composition all that much. Here's a technique that you can discuss. So if we have degree of the polynomial, if it's a rational polynomial function, so meaning that there's a polynomial p of x divided by polynomial q of x, such that the q of x has a degree that is at most the degree of the p of x, meaning that the numerator's degree is greater than or equal to the denominator degree, then you can simplify it. You can simplify it, try to simplify it, and you can come up with a polynomial where there's a fractional here and so forth. Not going to go deeply into these details. If there's another one, you know, the degree here is smaller than the degree here, then you can factor the numerator and denominator, and you can factor the denominator. Then like this, you can express it as something over x minus 2, something over x plus 1, and then solve this for a, b, and c by multiplying this back together and making sure that the numerator is the same. This technique is something that was taught in earlier courses, I hope. I'm not going to spend time here, but I just mention it here. You can look at it and you can find the technique, how it's done here. The equating the coefficients and so forth. And it's probably something that you might want to do. And then with that in mind, when you come to a sum like this, these terms, let me show. For example, these terms here, are all easily integrated. And then you come up with an integral in the end, and you get some logarithms there probably. Okay. All right, we're running out of time now. So this week's, this lecture, if you will, we conclude at integration techniques. So we discussed earlier in the first part, we discussed the fundamental theorem of calculus. Then we talked about substitutions, integration by parts, finding the integrals of trigonometric functions, and then partial fractions. And then we'll look at these other strategies for integration on Friday, and we'll get back to, we'll get to talking about differential equations on Friday. After that, we spend next week talking about differential equations, and then we talk about the sequences in series. And in the last week, we kind of pull it all together and try to make it into a coherent whole, a coherent story here. All right. Are there any questions now?
I wanted to ask if, will you upload to Moodle the recordings of previous lectures?
Yes, but the problem was that in last week, the Tuesday lecture was cut short. So I'm going to upload what was recorded, and I'm going to upload also this recording and all that. I'm sorry it's been taking a little bit time. I'm not going to stop this recording, by the way, because this is no longer new topic.